it's basically that. Now it's important because we are here. That's why we find it important.
Exactly. Well, that's a fundamental thing of any living organism. If you have the ability to prevent your own demise, you're going to do it.
Yeah.
The thing is that even if we get to Mars and even if we populate the universe will end.
Mm-hmm.
Yeah. I don't
probably.
think the way we are doing things, I don't think we deserve the chance to colonize another planet just yet. Throw this away.
Elon deserves it.
Yeah.
That obelisk that was found in the desert. I'm like, oh, Elon, you forgot something.
Yeah, and I would take the idea of deserve out of that, because there's deserve has nothing to do with propagation of species.
Can you guys just hang on for a sec?
Yeah.
Yeah.
Lawrence does have the permission to get in, right, Michaela?
He did when I checked. Unless there's another issue, I'll check again right now.
Oh.
He just
said hello in the Pangburn text. Michaela, can you give him directions, please?
Okay.
Or invite him to the room.
You going to have 504 sit on this with you?
Now everybody's going to be spamming Lawrence Krauss.
Manage user. Oh, okay. He needs... he didn't have any of these.
Let her...
So... Okay, he should be able to get in now.
Yeah, I think maybe when we go to assign roles, I think maybe it takes away the previously held roles, because deniability didn't have any idea why Bruce lost his whatever, but
shit, if anything, just give him God rolls for right now so we can get in.
That's what I just
later.
I mean, I just gave him everything he needs, so. All right, guys, we're standing by, so everyone just mute up for now. Hey, Lawrence, you made it. Just have to click that video icon there.
Can't hear anything.
I can hear you now.
You're breaking up. But I'm also I seem to be here as Lawrence, and somewhere else as LM Krauss. Should I get rid of LM Krauss?
Yeah, it's up to you. Either one's fine. I just gave all the permissions to Lawrence as well, whichever one you want to use.
Okay, I hear you now.
Yeah, great.
LM Krauss is your username, and Lawrence is your actual name.
Yeah, but I keeps coming
it's
on
the
and
same.
off. Keeps
if you go on to if you hover over the little action bar, it gives you an option to turn on your camera.
Right now, okay. Turn on camera. Okay.
There you go. And I'm going to solo Lawrence's camera here. There we go.
Use the wrong camera as usual, so let me just see if I can get the other camera.
Perfect, man. That's awesome.
Can you hear me?
Yeah, we can hear you good. It's good to see you. Can you see all of us?
Great to
see everyone.
Yeah.
I took all my energy just to get it.
Yeah.
Just to get in. So.
Well, we're very thankful, and I mean, first quick question for you: how has the COVID experience been?
It's not very good. I don't wish it on anyone.
Yeah.
Luckily, I have a serious case, but it's still worse than anything I wish on anybody.
Yeah, definitely. Okay, well, welcome everyone to the Lawrence Krauss Q&A. We want to maximize Lawrence's time. Please have your questions ready. And of course, because I'm just a bully, I'm going to go first. So, Lawrence, first of all, the release date, is it January 21st for the new book?
January 6th. The release date of the book is in the United States and Canada is January 26th.
Excellent.
And in England and the rest of the English-speaking world, it's February 4th.
Okay, awesome. And it's entitled The Physics...
In French, and January 26th as well for all people. But
gotcha.
I don't think the French version is published in Canada, so I don't know.
Interesting. Well, it would have to be in French Canadian, not regular French.
Come on.
Okay, first question. Were there any new or surprising discoveries that you made about climate change in your new book?
Yeah, there were a lot. I think I had fun going back over the history and seeing how there were some things that were known quite a long time ago. One of the remarkable things was come from a guy, Arvid Hogborn, in the 1860s, I think, who was in Sweden, but before Phineas Arrhenius, who's sort of the father of modern climate change, published his stuff at the end of the 19th century. But Arvid Hogborn had shown something rather interesting. He tried to estimate whether human combustion of human industrial activity could impact upon climate. And based on the carbon dioxide abundance in the atmosphere at the time, which they were able to measure at some rough level, he showed that if you took all of that carbon and made it into a solid, it would encompass a layer less than 1 millimeter thick on the Earth's surface, which he argued, therefore, since the amount of carbon that life is using is at least that much, he argued that life could be impacting on the carbon abundance in the atmosphere, and that was 170 years ago, which surprised me.
Amazing.
But the other thing, there's a lot of stuff, but I'll just give you a few other tidbits, which is that most people think that the greenhouse effect is really relevant at the Earth's surface. And while it is, it isn't. What really determines the effect of greenhouse heating on the Earth actually happens at the upper part of the atmosphere, where the Earth radiates into space. The equilibrium of the Earth's heating and cooling, the point where it remains constant, is such that this Earth receives energy from the sun, and then it radiates it back into space. And when the energy in equals the energy out, of course, things are constant, and that's when things are in equilibrium. And what greenhouse gases do, in effect, an increased carbon dioxide abundance in the atmosphere does, is change the point in the atmosphere where the atmosphere becomes transparent to space. And what it does is it makes it slightly higher in the atmosphere because the Earth's absorbing radiation a little more efficiently from the surface on upwards. The point where the Earth's atmosphere becomes transparent to space is at a higher elevation. And at a higher elevation, that surface is cooler. And since the Earth is radiating, therefore, from a cooler surface, it's radiating. The power of its radiation is less than it would be if we were radiating at a surface that was a little bit lower. And that effect causes the Earth to basically radiate a little bit less into space than it receives from the sun, which causes it to heat up. And obviously I described that at great length in the book, but what's really happening is that the Earth, and you can measure this, but the Earth atmosphere at the surface, at just the border of space, is changing. And that's and it's when you propagate things down from the surface of space down to the Earth's surface that you get the greenhouse effect. And what's kind of interesting is you can do, as I often like to do, back in the order envelope calculations, rough calculations of the kind of additional heating and change on temperature that can result from this increased carbon dioxide. And what's really interesting, and I love when this happens, is that some very basic arguments give you rough estimates that are not too far away from what we actually observe in terms of the additional temperature, that Earth's temperature increased by about 1 degree C in the last 70 years. And you can estimate that. And what I like to do and show people is that they have the tools. We actually do a little bit of math in the book, a little bit, to make these estimates yourself, to follow through and see, without supercomputer programs, how you can understand, based on the data, what's happening to the Earth's climate. And I think that's the fact that you can do that, the fact that it's based on really basic physics that you can understand, and is I think incredibly important. And now that, and I understood it in more detail, obviously, than I ever had before. I think that, and the last thing that may be surprising, there's a lot that may be surprising to people, but sea level rise, many people probably think of sea level rise as coming from glaciers melting, or from Antarctica or Greenland. And there is some of that. But what's kind of important to realize is that half of the sea level rise that's now occurring, and that's built in because it's already been there for 60 years, comes from the fact that water, when it gets hotter, expands. Yes. And that's been built in. And so the heat that's already been put in the Earth will guarantee, regardless of anything we do, essentially, between now and the end of the 21st century, that the sea level will rise about at least 1/3 of a meter, just due to the heat that's already been put in the Earth. And so there's nothing much you can do about that. And 1/3 of a meter is significant in various places around the world. So that there's no complex modeling going in there. There's no fancy supercomputer programs. It's just water heating up. And we've put the heat in the water already, and it's now equilibrating. And it will take more than a century for it to fully equilibrate. But that heat, as it equilibrates, causes the sea level to expand, and that's happening. And it will happen no matter what we do, more or less.
Very interesting.
Anyway.
And just a quick follow-up to that. Does the rising sea level worry you for humanity, or is this something that's easy to overcome?
Well, it depends where you are.
Right. You might have to move.
It's easy to overcome. Or it's worrisome if you're in a place that's below sea level right now. Yeah. Or at sea level. And since one of the things, I guess that's the other thing. In the last few chapters of the book, I show a bunch of new data. The book begins and ends in the Mekong Delta, where I was visiting with a group in January and really got my interest piqued in this. And the Mekong Delta is a rich, one of the richest fishing areas in the world. It applies to South Vietnam and Cambodia. Fish, and it, as I describe in the book, it's kind of a perfect storm for climate change. But I also show how independent studies, about just around the time I was researching the book, 2 different ones, showed that in fact, instead of being on average 2 meters above, or 1.8 meters above sea level, most of South Vietnam, almost all of it, is less than 1 meter above sea level. And in fact, a reanalysis of satellite images has shown that has basically lowered the distance above sea level of many places around the world, so that if you consider 1 meter sea level rise by 2100, which includes not just this heating, but also potentially melting due to glaciers and things, then a large number of people, somewhere between 160 and 200 million people, will live in areas which are below sea level at that time. Now, does that mean that they're destined to be flooded out? Not necessarily, but it depends on where you are and what's been done. Right now, if you live in Holland, you live below sea level, and most people live below sea level pretty well in Holland. But Holland is Holland. It's not Bangladesh, and it's not South Vietnam. And there are other impacts. So the bottom line is, yeah, it's worrisome. It's worrisome. Is it apocryphal? No, but it's going to have an impact.
Man,
and the impact it has will depend. First of all, how much sea level rise will depend, of course, on what other things happen for the rest of this century.
Right.
But also what countries do to mitigate the effects of climate change. As I discussed in the book, the book doesn't leave you. It's not a requiem. We as a civilization can do things, and technology can do a lot of things, but physics is what it is, and so we have to know what's likely to happen before we know how to deal with it. So yeah, I think it's a concern that we need to understand, and the countries that are most going to suffer are unfortunately the ones least capable of dealing with climate change. A lot of them in the mid equatorial latitudes, some of which are experiencing climate change in a direct way that can actually be measured on a daily basis, believe it or not, now, as I talk about it. There's a difference in weather and climate, but there's actually been enough data that in some places you can actually distinguish in weather climate change, which is a first. And there's another article I talk about in the book. So anyway, it's all comprehensible, and I think there are many other more speculative and worrisome possibilities that might result. I try and show people, as I talk about, it's kind of like Charles Dickens. I talk about the future as it will be, the future as it might be, and there's a distinction between the two. Some things are written in stone, and some things that Scrooge did were written in stone. But some things are possibilities, and we need to know that they're possibilities. And we need to ask whether they're possibilities that are worth risking.
Yeah. Okay.
Anyway, so that's maybe enough more of a preview than I was going to get.
That's amazing. I'm just drooling over here. I can't wait. We all will be purchasing this book, I'm sure, and I'll be doing lots of
blissfully short. Giveaways. Another thing I think science books should be as short as they can be and no longer.
Man, I agree on that.
Not history books should be thick, but science books should be thin.
Michaela, can you help Villain, please? Villain's waiting to get in. He just needs the. Okay, thank you. I want to go to Scott next. Scott, go ahead, and if you guys wouldn't mind, I'm tuning in from Vancouver, BC, as always. Just let us know generally where you are in the world, and if you can't let us know for security reasons, that's okay. Go ahead, Scott.
Yeah, I'm in Boulder, Colorado. Lawrence, I just want to know what do you think are the best options for sequestration of carbon that we have available to us right now? Because from what I've seen in the articles I've read recently, they say, or I've read, that we're sort of past the point where we can eliminate the negative effects to the upper atmosphere to develop clouds to radiate that heat, going forward.
Well, I mean, look, there's ways to. People are trying to work at ways globally to sequester carbon. I think it's science fiction for the most part to be able to. I was involved in one actually at ASU for a while, an effort to try and extract carbon from the atmosphere for $100 a ton, which is a challenge. But to do that would still cost many trillions of dollars to have an impact. We're talking about 10 gigatons of carbon.
Exactly.
Something like every year that we're putting in, and so I think that a friend of mine, in fact, in one of my podcasts, my friend George Church talked about sequestering carbon by designing microbes that would make plastic, and then using plastic as building materials. And he wanted to build like a bridge across the Pacific and little things like that. He's quite a visionary. But there are lots of options, and I think generally one needs to explore the different options and decide what's reasonable, and whether something is worth the cost. What's clearly important is to find ways to reduce carbon dioxide production in the atmosphere without negatively impacting on humanity. And and your definition of what negative impacting on humanity is partly depends upon your politics. And one of the things that I try to do very strongly in the book is talk about the science and leave people. Don't discuss policy at all in the book for a variety of reasons. But one is that I'm trying to reach a broad segment of the community, many, especially the people who view this as a liberal hoax, and don't want to feel told that they have to be told how to live their lives. This is a book that provides the information that you need to decide what policies should be done and read carefully about them. And one of the reasons why we're sending it to every member of Congress, I think, and a new Congress in January, since the book conveniently comes out around the time of a new Congress, we're trying to raise money and 600 copies for every member of Congress as well as the executive branch. And I think that hopefully that will be useful. But there are other possibilities. Talk about the upper atmosphere. There's a possibility of geoengineering, which has the advantage and disadvantage that it has a disadvantage and advantage that it can be done locally by one country, which is a danger, especially if people are worried about it. But the good news is that while it can be done by one country, unlike carbon dioxide, which stays in the atmosphere for between 600 and 1,000 years after it's produced in the atmosphere, aerosols will disappear in a year or two. So if there's some bad effects, they can be overcome very quickly too. So it has a disadvantage and advantage. And whether those are done or not, I mean, all of that will depend, it seems to me, on an informed public. And that's why I try to inform the public. Okay.
Awesome.
I do have sort of a follow-up question. Do you think we might be past the precipice of being able to claw our way back from where we are now?
Well, we are already past the precipice of being able to claw. Yes, of course, but we have in the last 6 years increased the carbon dioxide in the atmosphere by 30% in my lifetime. 30% compared to what it was. And that's remarkable in a single human lifetime. So yeah, you can't pretend what's done is done. Now, but that doesn't mean. But what's done is going to have some impacts. But that doesn't mean that the world is over. So when the IPCC sets a target of 1.5 degrees Celsius or 2 degrees Celsius. It's an artificial target that's set by, there's nothing magical or written in stone that says that the world is going to suddenly disappear if it's at that point. It's a target where it was felt that you could try, that the effects would be more limited than they would be if you went to 3 or 4 degrees Celsius, where you can imagine more things happening, severe things happening. So the bottom line is we're already past the point where we actually, I think, in all reality, and we're past the point of reaching we've gone beyond the target of 1.5 degrees Celsius. I think regardless of what we do at this point, there's a bunch of curves called I think it's called a ski jump curve that I show in the book that come from IPCC discussions, which is how much you would have had to cut carbon dioxide production each year to reach that target. And of course, the problem is every year you wait, because every year we're putting in an additional 10 gigatons. Remember, there were only something like 600 gigatons of carbon in the atmosphere, before human industrial civilization started to change that. And in any case, since every year we put 10 gigatons, it means every year that you wait, you have to cut it by more the next year. That's one of the reasons why it would have been nice to start the curve going downhill 10 or 20 years ago. Because we've already passed the point of being able to make the realistic cuts in a short time that will get us to that level. So I think. What was that?
Is that curve parabolic? So you made a motion with your hand that said, if we can get to a certain
no, it looks like a ski slope. I mean, the point is that it goes up, you reach a point, and you got to ask, in order to have the integrated amount of carbon dioxide goes in the atmosphere small enough, you have to cut down. But then every year you wait, the slope has to be steeper. And it's really quite evident. I mean, the book, by the way, has 75 figures in it, because I think the pictures are worth many words. And And there's a lot of good data you can show, and you can see the one look at this keystroke curve tells you why. People used to say, well, this may be a problem, but we should wait and solve the problem in 10 years. And the point is, in 10 years, it's a much different problem than it is now. If by then you put in 100 gigatons additional carbon, it means you have a different problem to deal with. Again, not necessarily a apocalyptic problem, but a different problem.
All right. Thanks, Scott. That was awesome. I go to my assistant, Michaela, next. Michaela, it's your turn.
Thanks for meeting with us. My question has to do with determinism and what you think is the correlation between the presence of determinism and sort of the alleviation of existential dread, if that makes sense.
Well, let me just say, I think the world is determined. I mean, I have no doubt of that fact. No, I'm more than thinking. The equations of physics are second-order differential equations that are deterministic, including the equations of quantum mechanics. So at a fundamental level, the world is deterministic. But the world is complicated. And effectively, at the level we live, the world is indistinguishable from a world in which there's free will. So while the world is deterministic, I believe we have to act as if we take responsibility for our actions. Even if there are myriad effects that produce the actions.
It's a fun game.
While we think we're happy, it's effectively indistinguishable from such a world in which we have free will. And therefore, we need to take responsibility for our actions. So that means we should not have, it depends. What it means depends upon how you take it. If that makes you feel better, that you won't dread that there's nothing you can do to change the future, and I don't think that's the case. There are lots of things you can do to change the future. Now, the reasons you change the future may be determined at some level by many, many factors, including your upbringing and other things. But you should go ahead and continue to try and make the world a better place and take responsibility for the things you do. And so effectively, the fact that the world is deterministic shouldn't change our goal and it is true. I think it is true that it's very hard to get an ought from an is, in the words of Hume. But I really think as I said before, without knowing what is, you can't know what ought. And I think ultimately you can come pretty darn close to using your brain and knowledge about the world to try and determine actions that are rational and I guess it's a presumption on my part that rational actions are ought. Does that answer your question at all?
Interesting.
It was interesting.
I don't think you should have an existential. I mean, if an existential dread makes you happy, then have it. I don't know what to say. But, I mean,
does existential dread make anyone happy?
If you look, existentialism had a huge impact on me when I was younger. Camus and Sartre did, and they continue to. I don't think there's any purpose in the world, nor do I think the world is absurd. But it's the world we're stuck in, and we just we make our own meaning, and we can't pretend it's cosmic. But it is what it is, and we have our time here to deal with it. And so, suck it up.
Yeah.
Like a true nihilistic absurdist. I like it.
Thank you.
Let's put some dirt on it and walk off.
Let's go to Matthias. Where are you joining us from?
I'm in Concepcion, Chile.
Chile.
Where?
Yeah, Chile.
Chile. Oh, hi.
Yeah. Hi. So I had a theory of how we can apply time in the universe, but I need some clarifications. So I heard you said one time about gauge symmetry, and that it doesn't matter the definition we give to things. Some things stay the same. So
yeah, things that appear to be different are really the same. Yes.
yeah. So if we apply that to time, and say, for example, that it is like this, like something that it's around everything, and it's one time, and it doesn't change. And relativity, it's when things interact differently inside that time.
Well, let me step back. Let me just step back a little bit, and because what relativity tells us is actually, it should be a theory of absolutes and not relativity, but because it really tells us that there are absolute things, but they're not. But it's not time or space. It's a combination of space and time called space-time. That the space-time interval between 2 points is the same for all observers. Different observers will measure different times between those events, or different distances between those events, because of their relative motion with respect to each other. But the space-time, the four-dimensional distance between the two events, point A and point B, in a four-dimensional world, it happens to be a four-dimensional Minkowski space, as it's called, but it doesn't really matter. That distance is universal.
Yeah.
As I described in one of my books, I mean, it's like the fact that if I take this as a ruler, it's and I turn it and I do this, it looks like the ruler becomes smaller because I'm projecting it onto the screen. That's because I have 3 dimensions. But we understand the length is the underlying 3-dimensional length is the same. The projection of it on the screen is smaller, so its 2-dimensional length is less. But if you could see it in all 3 dimensions, you'd see that it was the same length. And that's what happens in the real world in 4 dimensions. That we see different 3-dimensional projections of a 4-dimensional world, depending upon our state of motion. And sometimes it means that we see objects being smaller than they might be otherwise, and sometimes it means that we see time intervals being longer than we think they might be otherwise. But that's just our particular circumstances. But the underlying 4-dimensional space-time distance between event A and event B, located at place A and place B, is the same. And so there is a universality to time, but only in the sense that it can't be separated from space. That space and time are tied together in relativity, and they're tied together by your relative state of motion. I don't know if that helps.
Yeah, I wrote here or space and time because I thought that you may say that. So, with that being true, let's say that this is space and time, and everything inside. For example, I remember when you talked about a universe from nothing, that empty space is unstable, and when we apply time to that, we always end up with something. So maybe imagine that this is infinite. So there's everything that we experience now is happening inside this, which has no outside because it's infinite. So because
what about it?
I remember once in a talk, there was a model that was made of glass that it said that it could be infinite, and it had a loop at the beginning. But then they asked, what would be nothing there? And he said, what's outside? But what if that is everything and there's no outside? So
have to be an outside. That's the point. There doesn't have to be an outside. You can have a closed universe with no outside. Just like the surface of a sphere doesn't have an outside. It's just the surface of the sphere. The surface of the Earth is the surface of the Earth. There's no inside or outside. It only is if you embed the Earth and that surface in a 3-dimensional space. And so a closed four-dimensional universe, three space and one time, it can perfectly exist without any inside or outside. And probably the universe we live in is probably on the largest scales a closed universe, as I tried to describe in my book. Although it's not closed on a scale that is visible to us.
Interesting.
Mm-hmm.
The universe, we need no boundary whether the universe is infinite or finite. There isn't a boundary that you go to, and it's not like what was that Jim Carrey movie where he went to the end of the living in that
Truman Show.
The Truman Show. It's not like
found
you
the
get to
wall.
the end of the open the door and say that's it for our universe.
Wise Ape, how's it going, brother? You're up next. What question do you have? Just gotta unmute yourself. That's all right.
Okay.
He's just got sticky fingers.
Okay, you're doing sitting backwards to me, which is good. Okay.
Oh yeah, I think he's having a problem with his mic. Well,
your mic is working.
He's always on. I think
That's what usually happens to me.
Yeah. Okay. Well, I wanna throw one at you, Lawrence. That has to do. Maybe this is a simple question for you, but do you think there has always been, meaning infinitely always, the potential for something?
Well, I think there's always been the potential for something.
Yeah.
Well, that assumes there's been always been an always.
Dino.
The dino was around a finite amount of time, but anyway, so it assumes there's been an always, and we don't know. One thing is clear is our universe has a beginning, but it's simplest in our minds to imagine it being embedded in a multiverse which has always been in existence, or at least can be in existence for an infinite amount of time. In which case, if you wait long enough, a universe like ours will appear. But that's a question I just don't have the answer to. I don't know if there was a time, if there's a universal time and a universal space that transcends our own time, space-time. What I do know is that our universe appeared to have a beginning in time at a finite amount of time ago, 13.8 billion years ago.
Right.
If it arose spontaneously, as I think the evidence would suggest, and our best ideas suggest, then it arose. Then there was the potential for its existence, clearly.
Interesting.
And in that picture, it arose potentially from something else. Now, as I say, a lot of people get hung up on that. There may have been something else, but that's not nothing. Well, the point is, once again, I'm only interested in the existence of our universe. And there was no universe, and then there was a universe. And so there was nothing. There was nothing in terms of the space and time and everything that makes up our existence did not exist, and then it did exist. But whether there's something else is a different question. Someone else can write a book about whether there was something else. But
I just wanted to hear if you had a strong suspicion.
So
either way.
my personal picture is that there was always potential for this universe, and it's likely that some structure exists for an infinite global time in it. But I have no once one gets those questions, the laws of physics as I understand them break down, and so I can't give you anything more.
Right.
So
Okay.
rough estimate.
It looks like we got Wise Ape fixed. Wise, you go ahead if you can unmute again. There you go.
Oh, hello, Lawrence.
Hi.
ever meet Stephen Hawkings?
Of course, we were good friends. Yeah, we were friends for 30 years or so. And
Wow.
I've taken him many places, including bars and many places around the world. And my house, among other places, and his house.
What?
And yeah, so, and you know, we first were sort of office mates at Harvard many years ago, in the 1980s. He was visiting it. His office was next door to mine. And yeah, so we became friends over the years, and he was a remarkable human being, and a lot, and the most pig-headed human being I've ever known. Frustratingly so.
I do have a question.
That's the reason he was probably alive. But
Yeah, go ahead, Scott.
I took him.
What was the most drunk you ever? What was the most drunk you ever got with Stephen? What was the most drunk you ever got with Stephen? That's the important question.
I took him to a bar. I took him to a cowboy bar. I think I wrote about that once in Colorado. But what Stephen did to me, I guess I was drinking. Stephen, I was lecturing at Cambridge in England once. I was visiting for a week or two. Christmas time, I think, or Thanksgiving time, maybe. And I I had just been in Cambridge one day where I was wearing, for some reason, because I guess there's some fancy thing, I was wearing a suit and everything else. But Stephen invited me to High Table the next day, the day which I was giving a seminar, when I was wearing a T-shirt and jeans. And he decided that was the day to invite me to High Table at his college, which of course put me at a distinct embarrassment, because I arrived and they weren't going to let me in, because even as you know, even the young people are dressed in tails. And Stephen got a great kick of it. I think I had to take a rope or something, but you know, his attitude was, I was with him and therefore it was okay. And I think he got a great kick out of my being totally inappropriately dressed for that occasion, and yet nevertheless him having the power to be able to get me in, and to have me afterwards drink for drinks and things. But I don't remember Stephen ever getting drunk in my.
It's a good question, Scott.
But he enjoyed. Stephen enjoyed. I mean, Stephen was an amazing human being because he enjoyed. He didn't let he didn't let his infirmity. He tried not to let it inhibit his experiences, both his scientific ones, which is amazing, and every moment of every day was a struggle for him, literally a struggle, making my COVID seem like nothing, but he persevered through it in a remarkable way, and it was only when I was with him that it reminded how difficult his life was on a daily basis.
What do you, Lawrence? What do you think his greatest gift, just focusing on his work a little bit, his greatest gift to humanity was?
Well, I don't know. I mean, he combined arguments of quantum mechanics and general relativity in a way to try and understand the physics of black holes, and earlier work with actually Roger Penrose on singularities, which Roger just won a Nobel Prize for. But I think his work on demonstrating that when you apply quantum mechanics and general relativity, you get strange things, totally changed general relativity and took it out. Before Stephen, in my opinion, general relativity was an area of science that was sort of unique unto itself, and people studied it classically. And what Stephen's work did was brought it into the mainstream of physics in a totally new way, and made it a central part of our understanding of the fundamental structure of space and matter. And so he took relativity out of a sort of isolated corner of physics, general relativity, and brought it into the mainstream. And of course, the question of information loss and what happens when horizon of black hole have become central questions that physicists are still trying to deal with.
We do have Villain who joined us. Villain, do you have a?
Yeah, I'm not hearing anything. I'm hearing. Okay. Oh. I'm just hearing a little staccatic, alien-like talk instead of words.
I might have just be having a lag here.
And Dal as well. Dal hasn't talked.
Yeah,
Dal's
cool.
got a question.
I don't know if it's my.
We'll go
It's
to.
my-
Oh, sorry. Dal 2 is right up.
Oh, there it is. Okay. Now I can hear you. Okay.
Okay, cool. Yeah, I think we just got a bit of lag in the system. Dal, you're up next, brother. Go ahead with your question.
All right. I have a few, but I'll do the top one. I've been wondering. I've been watching Sean Carroll's Biggest Ideas in the Universe, and I've been wondering what your thoughts are on Hilbert space and whether or not it's real. He seems pretty convinced it's real, so I wanted your opinion.
Okay, I don't watch all Carol stuff, so but because it seems to me he makes much ado about very little often. But anyway,
I totally agree with that, by the way.
He makes this quantum mechanics seem a lot more. Anyway, so Hilbert space. What do you mean? Hilbert space is a mathematical space. It's a space in which
Papa,
is this.
oh, there's something important.
Hello?
Kaizen.
What?
Server mute.
Someone's talking.
Yeah.
Anyway,
sorry, go ahead.
So it's a mathematical space in which is a space in which one defines the wave functions that describe the universe. As such, it's as real as any mathematics that describes our universe is. Distinguishing whether it's, I mean, saying more than that is the kind of philosophical. I was going to say a worse word. It's a kind of philosophical discussion that may be of interest to some people, but it's just not of interest to me. Hilbert space is a necessary mathematical tool that describes the quantities that describe how our universe works. And in that sense, it's as real as wave functions are real. Or as real in some sense as space and time are real in the that a Minkowski space is real. It's the mathematical description of our universe. And this question of whether is mathematical description the same as reality? Well, it seems to describe our universe so well that there seems to be a one-to-one correspondence, and that's good enough for me.
Okay, great, Dal.
But,
thank you.
Thank you.
All this notion about the many worlds interpretation, as if that's interesting. I mean, that's 60-year-old stuff, and it's not interesting to me now any more than it was then. I mean, it's a classical way of trying to understand quantum mechanics, which by definition is therefore flawed. And there's nothing new and exciting about it. I think it is the best description of a classical description of a quantum mechanical world. A big deal. The better description is the quantum mechanical description. Right one.
That's some serious service by Lawrence Krauss. Eat
Yeah.
that, Sean.
Thank
So
you for
let's
that.
go to let's go to Kaizen. Kaizen, what do you got? And let us know where you're tuning in from, Kaizen.
Hi guys. Dr. Krauss, it's an honor to speak to you. I'm tuning in from New York, my bedroom.
New York.
But I've been reading up on the concept of superfluids and how space-time could possibly be a superfluid. And so if it turns out that it is a superfluid, would that be the missing point that we need to actually have a theory of everything?
Well, it depends what you mean by superfluid. As I've described in my book, Say the Greatest Story Ever Told So Far, the universe already acts like a superconductor. The Higgs field, which is this field that permeates all of space, basically causes the universe to act like it's a cosmic superconductor. And so it has interesting quantum mechanical properties that cause matter to have the properties we observe it to have. If it didn't have those, then particles wouldn't have mass, for example. But various people have talked about superfluids in different ways, as if there's some kind of additional dynamics to a field within space that has superfluid characteristics. And I don't know that that I don't follow that well, but it wouldn't necessarily lead to a theory of anything. It's just no. The answer is no, because what some people define as the theory of everything is a theory that explains the four known forces in nature and unifies them together: strong, weak electromagnetic force, and gravity. Right now, we have a complete theory of the strong, weak, and electromagnetic forces that are perfectly great theory called the Standard Model. We have gravity, which is a great classical theory, and don't yet have a clear way to unify it with the other forces. There are obviously string theory is one approach to try and do that. We don't know if it's the correct approach, but understanding the properties. But so a theory of such quote unquote theory of everything would be a theory that was a quantum theory of space and time. And saying space is a superfluid, I don't think is such a addresses the problems of understanding the quantum mechanics of general relativity. And therefore, it would not be in the language of what most people say is the theory of everything. I should point out, by the way, I hate the language, I hate the jargon, the term theory of everything, because it's actually a theory of almost nothing. Namely, a theory of quantum gravity and unified with the other forces of nature would allow us to understand two times: the beginning of the universe and the end point of black holes. Other than that, it's really kind of irrelevant. I mean, it's obviously important to understand the origin of the universe, but to understand the dynamics of everything else that happens in nature, you don't need a theory of everything. As my friend Frank Wilczek always said, what you need is a theory of something. And we have such theories. And so a theory of everything is never going to help you understand how oatmeal boils or why ice expands when it freezes. That's irrelevant. You don't need it. It was an unfortunate nomenclature, like much of the hype of string theory in the 1980s, that caught on, and I don't like the term. But in any case, it's not as if it's not important in an intellectual sense, but it really is important to understand the beginning of time and space and the end point of black holes, because those are the two places where quantum gravity becomes important. For almost the rest of, as far as we can tell, for most of the rest of what goes on in the universe, classical general relativity is a perfectly good description of gravity, and you don't need a quantum theory of gravity to understand it.
Excellent. Thank you, Kaizen. Let's go to Villain. Villain, go ahead with your question.
Hey, everybody. Thanks for having me in the room. Hi, Dr. Krauss. Nice to talk to you. I have no questions. I'm just going to listen. This is all over my head, so I'm going to listen and learn.
Okay, awesome.
Okay.
All right, thank you. I wanted to take one question, Michaela, if you wouldn't mind. One of the questions that you've curated from the interwebs. Go ahead.
I like how you said interwebs, implying that there is a multiverse even within the internet. This one's fun. Someone on Facebook said, if E equals mc squared in conditions where matter is quote unquote light matter, then does this equation still apply for dark matter when there is no light?
Yes. E equals mc squared doesn't depend upon whether something interacts with electromagnetic radiation or not. It describes the relationship between energy and mass that is universal for all massive stuff. So yes, absolutely. Dark matter behaves just like normal matter, except it doesn't shine. It doesn't interact with electromagnetic radiation. If dark matter is made of elementary particles, if they fall in the gravitational field, just like normal particles do, they follow the same trajectories throughout space, called geodesics, that normal matter does. And it has a different kind of interactions, like particles which are well known, called neutrinos. Neutrinos don't shine, but they also fall in the gravitational field, and they equals mc squared. And neutrinos would be great dark matter candidates if only they were dark matter candidates, but they're not. They used to be 30, 40 years ago, until we proved, and I was one of the people that proved they weren't dark matter, unfortunately. But they're the best candidates.
Good job.
That's a huge advantage. Is knowing they exist is a big advantage.
Right. Dal, I want to go back to you. Yeah, you said you had a couple questions. Let's go with another question from you, Dal.
We're going to go for just a few more minutes because
Yeah, we got just 6 minutes left there, Lawrence, and if we can steal you for that long.
I do have one question before it's over, if that's cool.
Okay, yeah, let's go to Dal, then we'll go Scott.
All right, Lawrence, what do you think of Roger Penrose and his conformal cosmology?
Roger Penrose is a very smart guy. I know him, and we once debated. Actually, he and I together at Oxford once debated a group of philosophers on the philosophy of science. When they made him my partner, I thought I wasn't sure that was a good thing, but it was fun. Worked out in the end. Having said that, obviously, Roger did profoundly important work on singularities in the universe. But he's done a lot of other work which is wrong. And I think almost all the other work that I know of Rogers is wrong. and his notion that there's any evidence of a past history of the universe, as far as I know, his original analysis that suggested in the cosmic wave background there was evidence of that was incorrect. And so I don't think his arguments about a cyclical cosmology, while they may be appealing in a mathematical sense, necessarily hold water as far as the actual universe is concerned. So I used to say, and now I shouldn't because he won the Nobel Prize, that he's a brilliant mathematician who's been wrong about every bit of physics he's done. But it's not, because he clearly did some important work. And he's a brilliant man. And his work on quasicrystals, new states of matter. He's really done interesting mathematics and twisters. And so he's been a profoundly important figure in mathematical physics. I don't think when it comes to applying it to cosmology, I don't think he's been very successful, in my opinion. And it's presumptuous for me to say that because his contributions to science have been, in general, profoundly important. Anyway,
Lawrence, before we go to Scott, I'll finish off with this one. Scott, go ahead.
I was just going to ask, I read something recently, I don't know if it's complete bullshit or not, but this talk of this, the idea that they've observed that the universe is getting hotter over time and the universe is not actually cooling over time.
I don't know of any such report. There's certainly, it depends what time you mean. In a cosmic sense, we can demonstrate that the universe is cooled. From the time the cosmic microwave background and now, we can measure it and show that it's cooler now than it was then. By cooler, I mean the temperature of the cosmic microwave background we can show has decreased over time. We can actually measure the cosmic microwave background at an earlier time and show that it was hotter then than it is now. So if people are talking about something recent, then that's interesting. But there's no evidence. There's no evidence the universe has heated up. In fact, there's much counter evidence, and and as far as I know, there's no good theoretical argument for why that should be the case. It's quite the opposite of every bit of cosmic thermodynamics that I understand.
Yeah, and I just pulled up the article and it said within the last 10 billion years is what they're claiming. It's from the Ohio State University, and it was published November 10th, 2020.
Did you say billion or million?
Million?
10 billion. 10 billion years.
Because I think the argument they're trying to explain a problem in having the Hubble constant. No, I mean it's definitely cooled in the last 10 billion years. There's measurement of that. So I don't know what the argument is suggesting, but it's an idea that, like most physics ideas, is wrong, right? Even if they're public.
So we've I'll finish off with this question, Lawrence. You just mentioned again being wrong. Would you say you were deceived by the Higgs particle?
Yeah, of course.
And why?
Deceived.
Why did it deceive you?
It's too damn simple. It's just it just seemed like the universe was a cosmic cop out to explain something as profoundly amazing as the masses of particles and the properties of forces that we measure. that a particle would that a field would condense in space was just the simplest possible explanation, and therefore I just thought nature would come up with something a little more exotic than that. And I was sure we would be wrong, but of course I was wrong about us being wrong, which is at least one time that I can say I was wrong.
Awesome. Well, we all wish you the best health, Lawrence, getting through COVID here. And please rest up. The world needs you. The world needs more Lawrence Krauss. And maybe next time we can get you on here and just talk about black holes the whole time, because I have a billion questions about black holes.
Or whatever. But maybe next time my book will be out already and people can have questions.
Yeah, that would be amazing.
Yeah, that's what I'd say. Maybe next time your book's out, we could talk about, that mostly.
Yeah.
That'd be interesting.
I'd like to. Yeah, I mean, because then people have something to chew on.
Yeah.
And hopefully encourage people. I can't say this enough. It's self-serving, but I really want to encourage people to order it because there's just a lot of pushback in this book because publishers didn't seem to want to publish the science as much as the emotions of climate change. And so I think the only way that it will have an impact is if people order it. And so I'm really hoping people will consider it.
Yeah, Lawrence, I'll be ordering a swack of them for giveaways and everything. So, thank you so much, Lawrence. We really appreciate your time.
But I hope but I wrote it with the hope that it have an impact. Okay, take care, everybody.
Thank you so much.
Yeah, thanks for talking to us.
Bye.
Bye. All right, guys, that was Lawrence Krauss. Amazing. Let's stay.
Holy shit, yo!
Feel free to stay in the room, guys, and just hang out. How do I get this back to just my equilibrium view here? Grid. Okay, there we go. Yeah, so that was fucking awesome. I'm gonna stop recording here.